Slide 1. Unlocking local LM control. Core thesis, llama.cpp is the foundational inference engine for most local LLM applications, offering unparalleled control and customization beyond wrapper tools like Ollama. Local execution step. Install llama.cpp directly via Homebrew, macOS/Linux or Windows to gain full control over your local LLM environment. Strategic return on investment metric. Maximize model performance and tailor behavior to specific needs, reducing reliance on third-party wrappers and their inherent limitations. Pillar 1. Why local models? Reduce operational cost associated with external AI services. Enhance data privacy and security by keeping models on premises. Maintain policy independence from third-party service providers. Pillar 2. Llama.cpp's core role. Recognize Llama.cpp as the underlying engine for popular local LLM apps. Understand that wrappers abstract away direct control and customization. Leverage direct access to bypass wrapper limitations and gain deeper insights. Pillar 3. Direct execution benefits. Access deeper customization options for model behavior and performance. Potentially gain earlier access to the newest model releases and features. Benefit from a lean binary with no background management layer, optimizing resources. Slide 2. Core engine and model format. Core thesis llama.cpp is a dependency-free C/C++ inference engine by GGUF, utilizing GGML for mathematical operations and GGUF as its self-contained model format. Local execution step. Familiarize yourself with GGUF models and the llama.cpp toolbox, llama/c, llama server for direct model interaction and optimization. Strategic return on investment metric. Optimize model deployment and resource utilization across various hardware, ensuring efficient local inference and maximizing hardware capabilities. Pillar 1. What is llama.cpp? It's an open source MIT licensed project with minimal dependencies, designed to run almost anywhere, Apple Silicon x86, Raspberry Pi, and major GPUs. Provides a toolbox of binaries like llama/sli, llama server, and llama bench for various tasks. Pillar 2. GGUF model format. GGUF is a single self-contained file format for LLM models, includes all necessary weights, tokenizer, and metadata for inference. Widely adopted on Hugging Face for efficient and portable model distribution. Pillar 3. The full stack GGML. GGML is a tensor library in C developed by the same author as llama.cpp. Handles the actual mathematical operations, compute graph, and hardware backends. Supports quantization, which is crucial for memory efficiency and running models on consumer hardware. Slide 3. Why go direct? Core thesis. Running llama.cpp directly provides total control over model customization and performance, making it ideal for single-user local deployments, unlike multi-user serving solutions like vLLMs. Local execution step. Evaluate your LN deployment needs. For personal or small-scale local use, prioritize direct llama.cpp over multi-user frameworks like the llm.cpp. Strategic return on investment metric. Achieve optimal performance and resource allocation for individual local LLM tasks, avoiding unnecessary complexity and overhead associated with larger systems. Pillar 1. Total control and customization. Gain access to all underlying tuning parameters for precise model behavior. Achieve fine-grained control over model output, personality, and performance. Unlock greater flexibility compared to the limited options in wrapper applications. Pillar 2. Newer modules and lean footprint. Potentially access cutting-edge modules and features before they are integrated into wrappers. Benefit from a minimal resource footprint due to its lean binary design. Operate without a background management layer, reducing system overhead. Pillar 3. Llama.cpp versus vLLM. Llama.cpp is optimized for single user or few user local inference on diverse hardware. vLLM is superior for batched, multi-user, GPU serving in high-throughput scenarios. Choose Ollama.cpp for personal local model experimentation and deployment. vLLM for enterprise scale serving. Slide 4. Fine-tuning model behavior. Core thesis. Llama.cpp offers 6 families of tuning norms including sampling, structured output, and tool calling to precisely control model generation and interaction. Local execution step. Experiment with sampling parameters, temperature, top case, top P, and implement JSON schemas for structured output in your local LL applications. Strategic return on investment metric. Enhance model reliability and predictability for specific tasks from creative writing to precise data extraction and enable advanced agentic capabilities. Pillar 1. Sampling controls. Adjust temperature to balance creativity higher and factual accuracy lower in model responses. Utilize top K, top P, and min P to refine the selection of tokens, preventing low probability garbage outputs. Apply repeat penalty to mitigate repetitive or looping behavior in generated text. Pillar 2. Structured output. Enforce strict output formats, e.g. JSON schema using the grammar flag. Physically constrain the model to produce only valid and well-formed responses. Crucial for reliable data extraction from messy text without post-processing or retries. Pillar 3. Tool calling integration. Enable models to interact with external functions and APIs using tool calling. Facilitate advanced agentic workflows and retrieval augmented generation RAG systems. Ensure OpenAI API compatibility for tool definitions, simplifying integration with existing ecosystems. Slide 5. Optimizing performance and hardware. Core Thesis. Advanced tuning knobs in llama.cpp allow for meticulous management of context, memory, speed, and cross hardware builds, ensuring optimal performance across diverse local setups. Local execution step. Configure any GPU layers and explore KV cache quantization to maximize performance on your specific hardware, especially for VRAM constrained systems. Strategic return on investment metric. Achieve higher inference speeds and run larger models on constrained local resources, extending the capabilities of your personal AI setup and reducing the need for cloud GPUs. Pillar 1. Context and memory management. Adjust the context size to control how much information the model can process at once. Quantize the KV cache, e.g. to Q8, to significantly reduce VRAM usage with minimal quality loss. Utilize techniques like rope and yarn to effectively stretch the context window for longer documents and conversations. Pillar 2. Speed optimization flags configuring GPU layers, NGL to offload model layers to the GPU, maximizing hardware acceleration. Enable flash attention, FA for a free speed win through a more efficient attention mechanism. Explore speculative decoding methods to accelerate inference, ensuring proper drafter model matching for optimal results. Pillar 3. Cross-hardware builds. Compile llama.cpp source code for various hardware backend CPU CUDA method. Split models across multiple GPUs or run CPU plus GPU hybrids to accommodate models larger than single VRAM capacity. Enable running large models in environments where it would otherwise be impossible, maximizing hardware utility. Slide 6. Local API and app integration. Core thesis. Llama.cpp's Ollama server tool enables serving local models as an OpenAI compatible API, facilitating seamless integration with existing applications and development ecosystems. Local execution step. Utilize Llama server to expose your local LLM as an OpenAI compatible API and integrate it with your preferred development tools or applications. Strategic return on investment metric. Unlock a vast ecosystem of AI tools and libraries for local model development, accelerating application building and reducing reliance on external API costs. Pillar 1. Serving local OpenAI API. Utilize Ollama server to expose your local LLM as an OpenAI compatible API endpoint. Allow local models to impersonate OpenAI, making them accessible to a vast ecosystem of tools. Enable direct interaction with local models via standard API calls, bypassing proprietary interfaces. Pillar 2. Seamless app integration. Connect external applications, e.g. Chatbox AI LangChain, by simply changing the API-based URL. Leverage existing OpenAI SDKs, libraries, and tools without modification. Build real-world applications against local models, fostering an independent development environment. Pillar 3. Deployment flexibility. Deploy Llama server by a simple command source build, Docker containers, or cloud environments. Choose your preferred backend for optimal control and to track the latest developments. Ensure reproducibility and portability of your local LLM deployments across different systems.